So hi, everyone. This is this weird concept where I talk and I don't know if anyone is listening. So just feel free to stop me and ask questions or add comments or whatever. My name is Shira. I am a new faculty member at the Hebrew University. And I just finished my postdoc at UC Berkeley with Professor Zilberman, who is there with you guys. I'm going to share a new study that we were working on during the past year. This is kind of a small part of a larger study, so I do hope to kind of get the message out there. Let me introduce you to the black soldier fly, those of you who are not familiar with. The black soldier fly is obviously a fly, but the interesting thing about it is that it is not a disturbance for people. It does not have a mouth, so it doesn't interact with food, it doesn't bite, and furthermore, it doesn't have any pest-like behavior. So many people tend to confuse it with the housefly, but it's a totally different concept. And the black soldier fly has several really important potentials or contributions to a possible to the bioeconomy. First of all, it's a protein-packed, very high quality, with a high feed conversion efficiency alternative to available feeds in the market. So it's an alternative protein, obviously. And the other interesting thing about it is that it acts as a bioconverter. So it feeds off of organic waste and turns it into protein and feed, obviously. If we look at the black soldier fly life cycle, you can see that it only feeds during the larval stage. And then once it grows, it stops feeding and focuses on breeding, on having eggs. But being such a protein-packed and high-quality alternative, and with the bioconversion characteristic, it has great potential as possible feed and in creating a sustainable food system. And the BSF market is really growing currently. It's happening because of different reasons. For example, decreasing global meat demand, obviously, the growing aquaculture industry, the increasing demand for animal feed in the industry, and for alternative proteins due to the rising prices of soy meal. And governments all over the world are starting to support the concept of using insects as feed and food, and we'll just barely discuss that in later on in this talk. So this industry is expected to reach $2.6 to $3.4 billion by 2030. You can see that it's quite a wide range. Also, the market size is estimated between 250 and $310 million. Again, it's pretty wide. I think this is a good point to say that the industry is not tiny, but it's not very large. And most companies these days are still keeping their information to themselves. I've been speaking to a lot of key personnel in this industry, and they're very afraid to share their numbers and their technology because you understand it's still a young, growing industry. What products are we talking about? We're talking about larvae that is being consumed living, dried, or processed. There's BSF protein meal, BSF larvae oil, and BSF frass. Frass is the leftover. So even from the leftover of the rearing process, we can make possibly fertilizer or even biogas. So it's really efficient. And currently the BSF is being used or intended to be used in the fish feed market, livestock feed, and pet food market. If you go on Amazon, you can already find BSF products specifically for the poultry industry. Now, one may ask, what about people? I asked that, and the people in the industry told me that they are not wanting to deal with the acceptance problems of entomophagy just yet. So given all the trouble and all the difficulties of being a new industry, they don't want to deal with having people grossed out or not grossed out, or interested or not interested. So they're focused on the feed market as of now. I did not encounter any company that is focusing on BSF as food for people at the moment. Perhaps there are some small ones, but I haven't met them. So, for example, the BSF can replace fish meal and fish oil. I don't know if you've been in the other session, if they discussed that. Aquafeed is one of the most environmentally impactful factors within the aquaculture sector. And this sector consumes most of the fish meal and fish oil globally produced. And so BSF meal could be a good replacement that is more sustainable in this industry. And not only can it replace the environmentally harmful food, but also there is just need for more food because there's a gap. Fish meal demand is exceeding the supply. So there's just room for it to fit in and fill the need, the demand that's needed. So just to sum up kind of the potential of the black soldier fly, it could contribute to sustainable food systems. It could contribute to biodiversity. It can help mitigate climate change because it's so efficient and it's a great alternative protein. And of course, waste management, and thus contributing to the circular economy, right? Because we have organic waste that's left over from production, and then the black soldier fly can consume it and diverse it into food. So this is something that we all hope to have, a much more circular economy. So we have this innovation and it's great. And now there's going to be a process of the public sector and the private sector and academia, where together they kind of form knowledge. So academia with the private sector are likely to conduct a lot of research, development, and produce this knowledge, where the public sector is in charge of having the policy to support knowledge production and support the development of the industry, given it has such good potential. The knowledge will be formulated into supply chains, and the supply chain is the focus of the rest of the talk. So I could probably talk about each of these circles in this specific picture for an hour, but I chose to focus on the supply chain. Now, the supply chain is also obviously influenced by policy and acceptance. If we map out the BSF supply chain, we have kind of supply material. Then we have the breeding stage, which is it's the stage where eggs are made. We have the rearing stage, the stage where larvae grows and feeds. Sometimes we need processing, sometimes no, but sometimes we need processing, but of course marketing. And because it feeds off of organic waste, we have another kind of stage or medium stage of waste collection before the rearing stage. Now, the thing is that because of the potential, the dual potential for both waste management and food, maybe vertical integration is not the best supply chain to maximize social welfare. So what we did in this study is we looked at the different options for supply chains. First, we mapped them. So if you look at this picture table, you can see the different stages of the supply chain. And then each color represents a different company or a different body that will do this stage, be in charge of that stage. Now, there's no relation between the different lines. So each line has its own colors. But if we look at the vertical integration, for example, then we have one company that's responsible for all stages. So it's responsible for the breeding stage, which produces eggs. They're responsible for getting organic food, for the rearing stage, protein, processing, marketing, and so on. Right? So this will be the most common right now in the BSF industry. Most companies are currently vertical A to Z companies. But we have these options of having different types of distributed systems where one company is in charge, for example, of producing eggs, and then the other is in charge of the rearing stage, and another, or the first one, of the processing stage. Now, instead of looking at all these lines, I'm just going to give a few examples. So, for example, we can have this interaction with farmers. Farmers have a lot of organic waste, right? So vegetable farmers obviously have a lot of waste, and also livestock farmers have a lot of organic waste. So we can have one company in charge of breeding, and then the eggs will be it would be sent to different farms and reared within the farm on the organic waste that's already there. And that would be a waste management technique. And then the waste would, the protein would either be sent back to the company for processing and marketing, or even consumed on the farm. Because, for example, if it's a livestock farm, then the cows or the animals could be fed from the protein that was produced on the farm. So here we're also looking at transportation that's safe and so on. And we have an even more ambitious idea. We can send these eggs to business centers and schools or prisons and jails or military bases or even restaurants. They all have cafeterias, right? And cafeterias have a lot of organic waste. Now, this could be an opportunity to get rid of the waste and even have even an educational experience in some cases, but it's just an external effect. And then these eggs would be sent to these cafeterias, reared over there, and the protein will be sent back or sold back. So there are a bunch of different configurations that could be possible for the rearing of the black soldier fly. There's also the nucleus plasma option, where there's one company responsible for everything, and it works with some contractors in some cases, and so on. But the question is, which one would be the most cost effective, right? So which one should we support as a government, for example, or which one we as business people want to contribute to or want to hope for? And the decision will generally be based on the source and quality and availability of organic waste and its location, economies of scale and policy. Now, what we did is we mapped out all these criteria that will influence the decision into which supply chain configuration one should attempt. So just real quick, some examples. When it comes to economies of scale, if there's economies of scale in rearing and processing, this will push towards vertical design, because this means more like a large plant where you need everything, machines and so on. But there's an issue with breeding. So breeding is actually the least stable stage of the production. Producing eggs is something that's it's not obvious, right? You need to have animals produce eggs. It's not obvious, and it requires skills and time and space. And it's not only the biological skills, you also need engineer skills and understanding. And when I spoke to the very few companies that specialize in breeding, they swear that their numbers of eggs are much higher than those of the A to Z companies because they specialize in the breeding stage. And because it's such a difficult stage, one should focus specifically on that stage in their production. So if that's true, then perhaps a diversified system is more important or more cost efficient than the vertical system. Another thing to look at is the issue of transportation. Because if we're talking about transporting eggs or transporting waste, we need to analyze and calculate the numbers and see what's better, what's more, what costs more and what costs less, where are the greenhouse gas emissions more, and what's more efficient. And then there's a question of where are we sending the eggs to? Because if we have a few large sources of organic waste, we can place our plant in the middle of these sources or close to them, or it might be very easy to transport the waste. But if we have many small, medium-sized locations, like small farmers, for example, then we have a great potential for poverty alleviation and waste management, but it may not be cost effective. And there's also a question of traceability, right? Because if I produce eggs, then I want my reputation to be high, and I want to make sure and keep track of the quality of the organic waste that my eggs will rear on, my larvae, because that's my name. And this may be more difficult when there are a lot of sources of waste. And the last thing that's like a big issue is obviously regulation, because harder regulation makes it necessary to monitor the waste source and pushes towards a vertical plant. And today there is regulation when it comes to to growing insects. So it's pretty recent, right? But in Europe, for example, when invertebrates are grown industrially, they are considered farm animals as of, I think, even 2021. It's pretty new. And accordingly, the use of animal manure and catering waste or former foodstuff, meat, fish, it's prohibited. So they can only grow BSF using vegetables or maybe, organic waste like cartons. And in the US, it's pretty similar. So right now, most of the companies are using vegetables, and that's problematic because it has a lower content of nutrient and it's obviously seasonal availability. But on the other hand, there are safety issues. So governments are not sure if the BSF is a good enough factor that can get rid of diseases, pathogens, drugs, or whatever that's in the food. So that's another issue that will kind of formulate the supply chain. And then the last thing is trust and acceptance. First of all, if we're talking about a diversified system, then we have to have several companies or several bodies working together, and they need to trust each other. If I have a vertical plant right now and I'm thinking about using a contractor to give me eggs and stop doing that in-house, I have to trust that contractor that he will supply me with the eggs. And speaking to people in the industry, we understand that there is no trust right now between the different companies, probably because it's a new industry, right? So currently, it's kind of each player for himself. And obviously, when it comes to insects, there's always the issue of public acceptance. And that's not only outside of the industry, with the consumers, but even within the industry. For example, if we're talking about farmers having to rear larvae, well, one might say, I've worked with vegetables and tomatoes, and I'm not interested in working with larvae right now, because that's not what I signed up for. People have wishes and people have opinions about insects, and it's something that this industry has to work with. Now, I said that we're not gonna kind of dig too much into it, but I do want to touch upon the issue of policy and market failures. Obviously, there are several market failures here. So we have the issue of public good and the knowledge that's being produced. But we also have a lot of externalities. While producers are currently producing this insect for feed, there are so many positive external potentials, like what we discussed before, even the waste management, the sustainable food systems, biodiversity, climate change, and those need to be accounted for by policy, right, and by the government. So now the government has a great job of trying to figure out what would be the correct policy to foster this industry because it has such a great potential. So just to kind of sum up this short talk, I think I did it in 10 minutes. That's what I was told. So just to kind of sum it up, we're talking about this new industry, pretty new industry with great potential, both for the environment, for food security. And we're trying to understand what would be the best supply chain form for this industry. And the first stage was to map all the factors or most of the factors that really influence the configuration of the supply chain. And that's what we did. And then our next stage would be to build a model and actually calculate the different factors and see what we learn, what we understand. Now, I do have to say that, there's learning by doing, and it's probably going to change over time. So it's likely that right now, most companies will still stay vertical, but maybe with time, as they learn and as they acquire more knowledge, this industry will get more diversified. And then these external effects will have more body and a bigger part in this industry. So we do have to see kind of where it leads and where it goes. And that's it. I'd love it if you have any questions. And yeah, thanks.
Okay. Well, not too far away from the trust issue that Shira was talking about. This research was actually spearheaded by colleagues at the University of Costa Rica. they actually genome edited a variety of rice to be resistant to drought. But obviously, what good is a technology if consumers will not accept it in the end? So just to give a little bit of background about the Costa Rican situation with rice and the rice sector, Costa Rica's northwestern province of Costa, which is part of the Central American Dry Corridor, is an area where there's oscillation, and it's called El Niño or La Niña effect in Spanish. This has become more intense over the last couple of decades, where it's a little bit more unpredictable. Statistically, there is a little less rain falling in this region. The CADC, or the Central American Dry Corridor's geographical area, varies and it impacts food security. This has always, it's a natural feature of the region, but obviously given climate change, it's become more acute in its drought period, and the rain is less well distributed and not benefiting crops so much. And of course, droughts are exacerbating already present social problems, making things a little bit more complex for the Costa Rican government. Given all these facts, it's also important to note or remember that half of all the people in the countries of the CADC spans, which goes from the south of Mexico to the northwestern part of Costa Rica, which is about 10 million people, live in poverty. Of those, 2/3 live of rural areas, live in poverty, and of those, an approximate 2/3 have an inadequate nutrition. So of course, this is a very sensitive issue for Costa Rica, and scientists were obviously very much interested in being able to develop a rice variety that would be more resistant, or at least give farmers a better chance of anticipating the effects of drought. So as I explained, Costa Rican scientists actually have applied CRISPR-Cas9 with the aim of developing drought-tolerant lines. And as far as we understand from our colleagues, inside of growth chambers, they actually do now have varieties developed. Now, of course, drought is a multifaceted issue. Obviously, the lack of water is an aspect, but also anticipating what the rain patterns will be is no simple task. So that prompted researchers at the Center in Molecular and Cellular and Molecular Biology at the University of Costa Rica to act. The overall aim of their research was to increase food security, of course, anticipate climate change, and the central question in all of this, the question mark, of course, is how will consumers react? So in 2018, scientists actually got a grant from the Costa Rican government to be able to survey Costa Rican consumers all over the country, their perception of genome edited rice. And with that, I'll talk a little bit about the rice sector. So as I said, in the northwestern part, that's where 62% of all rice is produced. That is directly in the area that the Central American Dry Corridor oscillates. So where 62% of rice is produced in Costa Rica is under the constant threat now of drought or rain that's very intense and not of much benefit, because it's either too much in a short amount of time, which damages crops, or of course the drought aspect, which is not enough water when it's exactly needed. And so of course, the country has actually taken out loans from the Central American Development Bank to be able to develop irrigation projects, which of course are in the hundreds of millions. And for a country like Costa Rica with many social issues to address is not the most practical and sustainable of situations. With that, according to the Costa Rican Rice Statistics Service, we can see that production over the last 5 years has actually tended to decrease a little bit. Area harvested has more or less stayed the same, and yield has had a less than ideal path over the last 5 years. And we wanted to make the study as representative as possible of the Costa Rican scenario, or of Costa Rican statistics. We could have easily gone to FAO stat, but we decided to go with the statistical service of rice producers in Costa Rica to be as realistic as possible, because FAO statistics aggregate and then they do all sorts of patchwork to be able to develop statistics, right? But yeah, yield over the last 5 years has not been the highest. It's about 4.1 metric tons average per hectare. So the methodology, it was a structured questionnaire of 25 questions. That questionnaire was actually developed by the University of Costa Rica, and the statistical analysis, which we can get into if you anybody would like to know more a little bit about that, was done by our colleagues in Costa Rica. It was face-to-face interviews, and 1,096 people all over the entire country were interviewed. Given that no personal questions or anything like that was asked, it was simply their perceptions of genome edited rice and genome editing in general. There was no need to go to to obtain permission or an ethical approval from the University of Costa Rica, given the norms and laws in Costa Rica. The only real constraint to the survey was that people be over the age of 18 to answer the questions. So, so in the demographics, mostly women were actually answering the questions, so 52%. Most of the respondents were over 50 years old, and the way they proxied educational level, they asked, they classified it into three categories: primary, secondary, or university. As we can see that most people were in the primary or less educational level. And the area of residence, so they did actually do it literally all over the country, so both urban and rural areas. And so most people obviously were in urban areas, as to be expected, right? Most people now live in cities, but they did actually venture out to the rural areas. Now, we have to say that before people were actually interviewed, there was a small paragraph that was read to them as to what genome editing was. So they read this paragraph, which says that genome editing is a technology that allows genes to be corrected in humans, plants, or animals. In the future, the possible uses of the technique could range from the improvement of crops to make them resistant to diseases, improve their productivity and national profile, to curing diseases in humans and animals. That should actually say nutritional. Apologies for the typo there. Okay, so then after that was read to them, then they were asked to agree with certain questions, right? What was their level of agreement? Obviously they were given 4 options. So when they were asked, well, whether rice can be used to produce climate-proof food, of course, most people, 67%, were in favor. Whether it was to save animal species in danger of going extinct, 76.7% of people were actually in favor of that, which is fairly interesting. Well, and then to eliminate mosquitoes as disease vectors, most people were in favor of that, 82% basically. And of course, if anybody's familiar with the tropics, dengue, Zika, all these diseases are real situations that people need to be aware of in the tropics. And so, of course, we would be very surprised to find out if people were against using genome editing to be able to address those issues, right? Now, to reduce the use of fertilizer in agriculture was interesting. Most people are actually in favor of that, which again, well, we can talk about that more in the Q&A. Now, where things started to get a little bit more interesting was when the Costa Rican scientists decided to ask more in the vein of, well, what does this mean for editing in humans or for human applications of this? And so, for example, in the scenario of to avoid a baby inheriting a birth defect, 74.2% of people were in favor of that. To produce pest-resistant foods, 76.7% of people were in favor of that. And to cure diseases in animals, 83.2% of people were in favor of that. To eliminate antibiotic-resistant diseases, which are now every so often, one will read that in the news, basically 84% of people were in favor of this. Where it got a little interesting was to produce food with a better nutritional profile, 78% of people are in favor of that. But where people were very much against was basically designer babies. That's where people seem to draw the line. So to elicit baby or to design babies basically with specific characteristics like gender, eye color, intelligence, it's very interesting to see that dichotomy or break in people's line of thinking, where they're very much, most people surveyed here anyway, were very much against that. Then people were asked a different set of questions where they were asked about, well, what benefits do you expect once genome editing is available in the country? I do apologize. The translation from Spanish to English makes it sound like it was a statement, but in Spanish, it actually is a question. So maybe I could have done a better job of translating that, but such as translations, right, from Spanish to English. So people were asked, well, what about agricultural productivity? Do you think it'll increase? Most people were in favor of applying genome editing for that. Do people think that it will benefit animals inside the country? Most people thought that that was the case, 68% basically. It will improve the health of Costa Ricans in general. Most people were in favor of that as well. And then the nutritional profile of food, people are very concerned about that kind of thing in the tropics, obviously. And so most people were in favor of applying genome editing to that. Now, as for the potential risks, this was a different set of questions that people were asked. Do people think that there's a risk of harming the quality of life of animals? And most people in that question responded that no, 37%. Whether there's a risk of producing an environmental damage, people that should be 35.5%. Most people thought that there's a low chance of that, but the high percentage was also notable, right? It's about 25% of people, according to the sample. Risk of agricultural products harming human health. Most people thought that that was low, but again, we must remember that they read a paragraph, and it's actually interesting that during the opening of the conference, if anybody remembers that, Jack Bobo said, well, it's one thing what people tell you, it's one thing what people say, it's another thing entirely what people actually do. So I think that results like this should be taken with a grain of salt. Nonetheless, what are the negative effects for descendants? And by that proposition, what's meant is like, what is meant for the next generation of people, right? And so people think that there's not much risk of that, of applying genome editing to that. Now, the scenario under which consumers would consume gene-edited rice or beans, because both are staples in Costa Rica, if it were available in the country, 51.7% said yes, they would consume them. If the price was the same as conventional rice or beans, 65.5% said that yes, they would consume it. In other work I've been involved in, Canadian consumers also expressed that opinion that if the price was the same as a conventional equivalent, that people would be willing to consume. Again, whether they actually do it or not is another matter entirely. But at the very least, people expressed the idea that they might be enticed to consume given prices, and especially in the context we are now, where food inflation is reality. Of course, perhaps results would change due to that. If the nutritional value, so a different way of asking the nutritional profile of the food gene edited, was better than conventional rice or beans, would you consume that? A lot of people said, well, as you can see, 70.5% said that they would. So in conclusion, Costa Rican consumers seem willing to consume gene-edited rice. They are open to genome editing technology, except when applied to humans, designer babies. It seems to be an international really perception that designer babies are where people draw the line in these types of technologies. And Costa Rican consumers, scientists, can take this survey as a signal to continue at least their research. But again, going back to something that I thought was quite insightful from Jack Bobo in his presentation at the beginning of the conference was, well, it's one thing what consumers say, it'd be another thing what they actually do. So at the very least, it's a signal that research should probably continue. So with that, I would take your questions.
Okay, I've been told I've got incentive to finish early. At least there's at least one beer involved, right, Stuart? So I'll keep going. So this presentation is, maybe I'm saying something really obvious, but I think I'm saying something different than what's out there in the rest of the world. I better shrink this so you can see my presentation. Obviously, the biosphere management is really important right now. Not only we're not meeting our greenhouse gas targets, we have real record high real food prices, and my whole point of this presentation, perhaps, is encapsulated here, is that in the current national inventories of that we actually don't measure CO2 in agriculture. the CO2s that crops take up and the CO2 that crops that re-emitted as those crops get used are not included in the accounting systems. It's a bit striking, given that. Yes. So CO2 that's emitted through through human or animal respiration, which from eating food is not included. CO2 from burning biofuels is not not included in the framework. And the CO2 that's sequestered annually by crops, that then it's in turn eaten and digested, is not included in the system. It's outside of the accounting system. So the question I ask is, should national accounts include harvested crop CO2? We want to include soil sequestration, but should we actually look at the CO2 that's in harvested materials? And how would that change the way we look at this? So I'm arguing that it should be there. Does it matter for policy? Does it matter for climate change? I think I've got 15 minutes, maybe 10 to convince you. So I'm going to try to convince you. Yeah. Okay, so I'm going to look at this both theoretically and empirically and discuss a few policy options. So first of all, it's very clear the international leaders have said, we're worried about the concentration of greenhouse gases in the atmosphere. That's what we want to lower. That's the stock we're after. And so we've identified what we want to change, and we've identified a number of emissions we want to keep track of. Methane, nitrous oxide, carbon dioxide, even carbon dioxide from land use changes, and certainly from fossil fuel consumption, but we have specifically excluded all of these respiratory forms of CO2. It's just part of Flux, it doesn't count, but of course it's a big part of the managed systems. So I think what that means is much of the bioeconomy related to harvested crop carbon is invisible to policymakers. They can't see it. For example, if you were to magically come up with biotech to double grain output in North America, it wouldn't show up in the accounting. And yet there'd be a massive influx of carbon here, and it would basically feed the world to do something else out there, but none of that would be measured within the system. And I just want to point out these fluxes are big. Through photosynthesis, plants pull in about 120 million tons of carbon a year that basically gets cycled. Human emissions are 9, maybe up to 14 if you take the most current from fossil fuel emissions. So this is a big amount of flux that can be controlled that we're not currently controlling. We're certainly controlling, but we're not measuring a chunk of it. And the other thing to point out in this picture is if you look at the carbon stocks, soil carbon, for example, is 2.3 billion tons of carbon versus 800 million in the atmosphere. And fossil carbon's bigger than that. The oceans are bigger than that. So we're really talking, all our policies have been focused around this human burning of fossil fuels almost, with some additional pieces for methane and nitrous oxide. I'm not the first one to think that it might be important to keep track of where carbon flows. Hayes did this for North America and looking at from 2000 to 2006. And what they did is they said, let's look at the agricultural systems and particularly forest crops and other products and see what's happening to that flux. Where is the carbon actually going? And what you'll see here is that in forest lands, the blue and green areas are actually areas where the crops are pulling net amounts of carbon out of the atmosphere. And the red areas are where on net, you're putting more carbon back into the atmosphere. So for example, when your corn grows, it pulls air out, it pulls CO2 out of the atmosphere, gets moved over to livestock in Texas, it gets emitted, and it shows up as red in Texas. And you can focus a bit more, you can see the rate of that sequestration, it's a touchscreen, is most intense in the Corn Belt. in terms of just because of the amount of grains, et cetera, that are being produced there. And of course, it's the intensity is biggest, and the emission intensity is Texas, where it gets fed, if you like, some of the least. These are the totals they came up with. They said that, you know, croplands, Canada were pulling out 32 million tons a year that weren't being accounted for. The US croplands, 264 million tons. They added forest to that. As a result, they said North America agriculture and forestry pulls out 327 million tons of carbon a year that's basically pulled out of the atmosphere over North America and is emitted somewhere else in the world. They've already taken into account all the US emissions related to that. This carbon is emitted somewhere else in the world. And by the way, when we export coal or oil, we don't count the emissions of where that, we don't count foreign emissions from that. We only count our own emissions. But for grains, these guys are saying, well, yeah, we pulled this out of the atmosphere, but it's going to get re-emitted anyway, so we should count it for ourselves. It's a bit strange. Okay. So basically, if the objective is to manage atmospheric CO2 concentrations, then all emissions and sequestrations have equal external marginal costs and benefits. Emissions that are not measured in national accounts will not be reflected in domestic mitigation policies. If you don't measure these things, they won't show up in your accounts. And certainly sequestration is not measured in North America will not be reflected in policy. And the second thing to think about policy is, so things you're not measuring, you're not going to manage. And secondly, the Paris Accord is not comprehensive. There's a bunch of countries outside of the Paris Accord that can behave as pollution havens, if you like. Okay. So where does that leave us? So our current policy for the bioeconomy is indirect. We tax fossil fuels. We say biocarbon doesn't count. We're not going to count it at all. That creates an artificial demand and incentive for policymakers to improve their national accounts by taking grain and turn it into biofuel. And by that way, they can reduce their fossil fuel emissions, and the extra emissions for biofuel doesn't count. What's that do? So just to be clear, getting back to here, we do count emissions from agriculture. We count nitrous oxide, we count methane emissions, we count actually soil organic matter sequestration. These are all really hard things to measure. Carbon in grain is easy to measure. We don't measure that. We ignore that. So it's not a measurement issue. But in effect, our system makes these CO2 flows, basically grain is CO2 that's pulled out, put into harvested grain, moves other places, and emitted as CO2, those don't count at all in emissions. What does that do to the world? It increases the derived demand for grains in the Paris Accord countries. They all have incentives to improve their national accounts, so they take biofuels, great biofuels, look how great we are, etc. That increases the demand for grains. At the same time, they said, well, we want to actually limit input use, tax fossil fuels and other things for agriculture. That reduces supply a bit. That collectively reduces the excess supply from the Paris Accord countries, raises the world price of grain, and we know the rest of the story. We create incentives to burn rainforests, to create more land, and we also create food insecurity issues. But it's related to this idea, we're using a totally demand pull system. The way we incentivize the bioeconomy is by taxing fossil fuels, creating the demand for grains, but we don't actually keep track of what's happening on the biofuel side. If this is net ecosystem production with harvest, we have policies like that, then we would recognize when you pull carbon out of the atmosphere, that has value. So we'd actually subsidize the production, we'd encourage and subsidize the production of grain, and we turn around and discourage the use of it. That's how you would price that externality if you were worried about both sides of it. Okay. If you did that, you'd flip this thing on its head. You're basically saying grain production is good, grain use is bad in these Paris Accord countries. Again, when it makes sense logistically, but this would have the effect of lowering the world price of grains, which would help food security, reduce the incentives to burn rainforests, and it's a more complete pricing of this externality. Clearly, if emitting something in the atmosphere is bad, pulling carbon out of the atmosphere is good. None of this is accounted. Okay. So what I'm arguing is that this is what the world looks like when this is sort of moving to the next part. Is this important? This is what the Canadian accounts kind of look like when you just use the national accounting as it currently exists. You get 16.4 million tons in soil organic matter. That's a negative. Atlanta may have a bigger number, but it's a number. Similarly, nitrous oxide emissions are there. And similarly, you have methane emissions. These are the parts that show up in our national accounts, and I included land use change in this. Basically, agriculture emits about 36 million tons a year. That's what it looks like through a UNFCCC accounting rules. This is what greenhouse gas emissions look like from Canadian agriculture over time with that accounting system. If you do account for the carbon that goes into grain and the carbon that goes out of grain, you get a totally different picture, which you can add to these effects. And so basically, cropland in Canada, this is harvested grain, basically, contains 157 million tons of CO2 that's been pulled from the atmosphere. Some of that shifts over here and is emitted in the rest of Canada as livestock and biofuels and other things burn that up. But there's a chunk that's missing, right? There's about another 70 some that's in export grain that's not emitted in Canada, it's emitted somewhere else. So that flips the sign around for net greenhouse, rather than being a source of emissions, is actually a net sequester of grain. And this demonstrates that, in part, the power of things like, if we can increase the productivity of land, we can pull a lot more carbon out of the atmosphere that has value to the world. And this system would show that would show up. It doesn't show up in the UNFCCC. It shows up in other benefits. If you take that number and look out over time, you get a totally different picture. You get one that's flipped from a net source to a net sink, and that sink is becoming deeper over time. Two totally different pictures, which I think is at least worth reflecting on. And by the way, this system is a lot simpler than trying to do life cycle analysis and all these other things that are proposed to try and fix our current accounting system. Just count carbon going both ways. I would argue that this incomplete system has led to funny policy design, maybe totally inappropriate. This is nitrous oxide emissions in Canadian cropping systems over time. They've gone up about 30%. So what's the federal government want to do? Let's reduce nitrous oxide emissions by 30%. But if you do this, what's going to happen to the amount of grain that's growing? What's going to happen to your neighbors? You beggar their neighbor type policies. I've heard that phrase this morning, Vince. So if we employ this and reduce the amount of nitrogen, what it does is it shorts world some grain, and they're going to emit more CO2 or have to do something different. I would argue under the current rules, much of the bioeconomy is invisible. And this current system leaves us with only demand pull there, which worsens food security, exacerbates pollution otherwise. We're already doing the difficult part of measurement. Methane, nitrous oxide, soil sequestration, those are hard things to measure. You could easily measure the calorie content in grain, You know how much CO2 went into that. That's easy. That's simple accounting. This is hard accounting. The hard stuff's being done. So I would argue you could do it, and you could start with a new baseline. You can do it historically. You just need FAO data basically to do this historically. So you could re-benchmark everybody where they were in 1990 and update the targets. It wouldn't be hard to do. And it would greatly simplify what we try to do right now to accommodate this, the fact that we're missing these indirect effects, because we'd actually be capturing them from the beginning. So that's it.